Welcome dear civil engineering viewers and students. Now I will be calculating the deflection under the load 60 kN that is applied at the center of the beam. Now note down that the part, suppose you take this as C and this support as B and this one as A. The part CB has twice the flexural rigidity when you compare it with the part of the beam AC. So now we will split this into two and we will evaluate the strain energy. Now you can see that the loading is exactly applied at the center. So the value of reaction at A could be taken as 60 by 2, that is equal to 30 kilonewton, and this is equal to RB because the loading is exactly applied at the center. So if you apply the summation of vertical forces, all vertical forces acting on the system equal to 0, you will get RA plus RB will be 60 kilonewton, and summation of moment at B is 0. Then you take RA multiplied by the lever arm distance is equal to 60 multiplied by the 4 meter as the lever arm distance. So you will be getting RA equal to 30 kilonewton as well as RB equal to 30 kilonewton. Now how to do this problem? So here we will first we will take X from the point A. Suppose you take this beam, this is A and this is B. Now here let us take the limit as X equal to 0, and at this location X equal to 4. So we will take X somewhere here. So this is X, distance X from the point A. Now moment X, moment at X, that is, we will consider this as X1, okay, that is equal to this reaction RA multiplied by this distance, lever arm distance X. So we will get RA into X, that is equal to 30 into X. Okay. Now similarly here we take the beam, the same beam is taken here, this is RA, and here you have 60 kilonewton, here you have 30 kilonewton as RB. Now take X from this location. So here the origin is point B. So at this location you have X equal to 0, and at this point you have X equal to 4 meters. Now mx2 equal to RBX, RB into X equal to 30 X. So the first half of the beam is integrated from A to C. So this is point C. The second half of the beam is integrated from B to C. So taking A as origin you evaluate mx1, and taking B as origin you evaluate mx2. Now finally the strain energy stored is equal to mx1 square dx by 2ei 0 to 4 plus mx2 square dx. The beauty of the equation is at this location particularly you will be having 2e times multiplied by 2i, because this part of the beam CB has twice the flexural rigidity when you compare it with the first part, that is AC. The limits are between 0 to 4. So now you can evaluate in any manner. I have taken A as origin for the first half AC, and for the second half of the beam I have taken B as the origin. So this is the total strain energy that we have to evaluate. Now how to do that? So here, what is mx1? 30x. mx2 is 30x. Okay, now the strain energy is obtained from this equation. So mx1 is 30x. So 30x the whole square dx by 2ei integral 0 to 4 plus 30x the whole square dx by 4ei. So why we have 4ei is that here the flexural rigidity is twice as that for the first half of the beam. So this is for 0 to 4 limits. This is part AC, this is part CB. Now here we have 900 by 2ei times, here x square we will have, so we will have x cube by 3. The limits are from 0 to 4 plus 900 by 4 ei into x cube by 3 having limits from 0 to 4. Now we have here, this is 1 by 2, here it is 1 by 4. So 900 into 4 cube by 3 multiplied by, so you can put a here, the flexibility, and inside this bracket you will have 1 by 2 plus 1 by 4. Now finally if we evaluate this, you will have 14,400 by 8. This is the strain energy Now external work done is half P delta equal to half into 60 times delta. This is equation 1. This is the equation 2. So now you equate 1 and 2. So 14,400 by EI is equal to 30 delta, which implies delta equal to 480 by EI. So this is the final value of delta for the beam where you have flexural rigidity for part CB is twice as that for the part A. So for the simply supported beam, finally the delta value is 480 by A. Thanks a lot for watching, and if you have any doubts, please mention in the comment section. Let me get back to you with problems on frames in the next lecture. Thank you.